All right, good day, everyone. Welcome to the AOML HRD Science Seminar. This seminar will be given by Dr. Xiaomin Chen, and I'd like to give a quick bio on Dr. Chen. He obtained his PhD in meteorology in 2015 from Nanjing University in China, at the School of the Atmospheric Science. Since then, he was also a postdoc associate with the Northern Gulf Institute, as well as with the National Research Council. And in September 2021, Dr. Chen became a research scientist with the Northern Gulf Institute. And he's very recently, is now an assistant professor at the University of Alabama at Huntsville. And so his title is Toward Improved Planetary Boundary Layer Schemes. Hang on, as I continue to read this. Schemes in high wind conditions using large eddy simulations. I'm going to put this in slideshow mode and take it away.
Okay, everyone hear me?
Yes.
Thank you. And yeah, so good morning and thanks for joining, like either remotely or in person, and appreciate that. And so today I'm going to talk about the project has been over the past 4 years. So we try to evaluate and improve the boundary layer scheme in the high wind conditions. And the initial motive about this project is like, so we probably even model when we do the forecast or try to simulate the hurricanes. Yeah, we will find there's a bunch of PBL scheme in the list, like in the WRF model or some other research operational models. So I have to convince myself I need to pick one of them and simulate the tropical cyclones. But even I did that, so I cannot convince myself like why we should choose that or why that PBL scheme would be my favorite. So today, the talk, I'm trying to give the answer basically using the large-eddy simulation and observation. So this is start from when I'm NRC postdoc and then become NGI postdoc and scientist. And I like to appreciate my co-author, especially my mentors, Frank George and Joe Jun and Pat. And I also like to appreciate my co-authors, Andy Gus and Chen, who provide a lot of support about the HAFS and even the post-processing processes. And this work won't become possible without the support from Shirley and Robert and everyone in the Hurricane HRD modeling team. So also my office mate give me a very good time, like to support, and we encourage each other over the past 4 years. I really appreciate that. And EMC Folix need to be appreciated because we recently implemented this improved PBL scheme into the HAFS system, and there are many others. Anyway, so let's come back to the talk today. So the background, so why we need to focus on the boundary layer scheme, so your tropical cyclone can be viewed as simplified as a current engine. So there are 4 legs. So there are one in the boundary layer, that would be from A to B. That parcel was affected by the boundary layer inflow from the large radii to the smaller radii. During this process, it absorbed the surface heat fluxes and increased the equivalent potential temperature, theta E. And then the parcel ascending in the eyewall and release the energy by radiative cooling in the upper troposphere, and then descends and conserve the theta E parcel to close that cycle. So from this cycle, actually the key part or the kickoff part will be in the boundary layer because it provides energy source here. And also meanwhile, and the boundary layer also is energy sink of the tropical cyclones. Remember, there's a frictional dissipation in the boundary layer. So both the energy like surface fluxes and also the frictional dissipation or involve the subgrid scale like turbulent processes that cannot be directly resolved in mesoscale the model grids. So they need to be parameterized, while previous study have demonstrated that there's this very big or large sensitivity of the model results to the PBL scheme. So accurately parameterizing the subgrid scale turbulent processes, especially in the hurricane conditions, is crucial to improve the hurricane forecast. So that's one motive here. And but unfortunately, the available PBL schemes so far are generally designed for the low wind conditions, like the convective boundary layer. The photo on the left just showed an example about the convective cloud developing upward and showing no tilt. So this is a demonstration about the low shear environment. And actually, in the convective boundary layer, the turbulence is predominantly buoyancy driven. But it's another story in the hurricane boundary layer. And I give an example about the photo was taken by hunters in the eyewall in the eye of Hurricane Michael. So actually, we just saw the stadium effect of the eyewall, and clearly the eyewall have a tilted substantially with height. And we can even see some spiral structures. Yeah, and this is clear evidence of the shear dominant environment. And in the hurricane boundary, especially in the lower to middle boundary, the turbulence is predominantly shear driven. So that different nature of the turbulent generation mechanism. So just remind us, when we directly apply the traditional PBL scheme for TC modeling, we have to be very careful about that. And the boundary scheme, it's essentially like a single column model. Its role is responsible for the vertical mixing, and it works actually in both atmospheric and oceanic boundaries. And for the PBL scheme, the output tendency of the momentum scalars and the tracers. So the vertical gradient of momentum stress, that would be W prime V prime. That's a subgrid scale of momentum stress. So it's a key task is to parameterize that in the PBL scheme. And they use the flux gradient theory, namely like W prime V prime relates to vertical wind shear. That's the mean wind by the Greek scale, and by a coefficient Km. So Km is a measure of the ability of turbulence to vertically transport momentum. And there's a negative sign from. This means this is downgrading transport. And so the task won't become like how to parameterize the Km in the PBL scheme. So we have to understand a little bit more about the PBL turbulence processes to address this issue. So the energy cascading in the boundary typically is like there's a wide spectrum of the turbulent eddies in the boundary. Yeah, so there's one specific type, and we call that as energy containing eddies. They have a scale is L. So these eddies typically have a relatively large scale and is most energetic because it contains like a lot of kinetic energy. And they get energy directly from the mean flow and transfer that to the intermediate size of the turbulent eddies. And this intermediate size, like turbulent eddies, further transport energy to the locally isotropic. It's very, very small scale. And this energy become converted to the thermal energy because of this cost dissipation. And from this process, we understand that like the vertical mixing is predominantly like contributed by energy containing eddies. And so how to visualize that. So I give an example about aircraft. So when aircraft fly through the clouds, the turbo engine will generate like a pair of vortices after that, right? And this diameter of this circulation, we can just visualize or interpret this as like energy containing eddies. So what the Km is determined, like if we have a large size of the energy containing eddies, so the vertical mixing will get stronger, right? Because the size is larger, and also the Km is proportional to the turbulent intensity. Like simply put, it's like circulation is stronger, the size is larger, the vertical mixing will get stronger. This is the basic idea to parameterize the Km, like in the PBL scheme. And I give a simple example about K profile parameterization scheme. So this is the first order PBL scheme because we don't have any prognostic equation for the high moment, like the turbulent kinetic energy, the equations. So it's basically, as long as we know the surface layer conditions, as long as we know the boundary height, we can prescribe the Km profile in between from the surface layer top all the way to the boundary height. And so in the surface layer, the Km will be equal to the gamma times z. So gamma actually is a constant, is equals 0.4, and z will be the height. This is actually the mixing length or the eddy size in the surface layer. So that means like in the surface layer, the eddy size increases linearly with height. And that's because the size is limited by the distance to the surface. And the farther they get away from the surface, the potential they get a larger size. So that is a physical limitation there. And the VWS, that's an additional variable. That's what we call the convective velocity scale. In the neutral boundary conditions, the WS will be equal to the frictional velocity. And so that's a measure of the turbulent intensity. So the idea, just as we said earlier, the Km is proportional to the mixing length, the turbulent size times the turbulent intensity. So above the surface layer, as long as we know the diagnosed boundary height h, the Km profile is prescribed. That's why we call this as a KPP profile. That was determined by additional polynomial term on the right. That's 1 minus z over h. Z is a height to the p power. The p is a shear parameter equals to 2. Yeah, this is a very important formulation because that basically positions the maximum of the Km at 1/3 of the diagnosed PBL height. And also the Km maximum of the Km is also proportional to the diagnosed PBL height. So that means like if we have a higher diagnosed PBL height, the maximum of the Kn will getting larger. So the vertical diffusion is getting larger as well. And meanwhile, the shear parameter also is determining this like Kn magnitude. If the value was increased, the maximum Kn will be reduced. So that's just the basic math behind this formulation, and I will emphasize this later. So the key task of the KPP scheme, as we know, the surface layer, we get the information easily, but for the diagonal PBL height, we have to determine that. So in the KPP scheme, they determine the boundary layer height using a bulk ratius number, and it's a non-dimensional measure of the stratification of the shear. So the stratification is on the Brugg facade frequency, and shear was calculated from the surface all the way to a specific model level. And but anyway, so we have some like red triangle here. Let's try to mark. This is the surface level. The height equals to 0. In the denominator, so the 0 is meaning the wind speed is 0, UH and VH. And I give a cartoon on the right just to show how this is determined in the PBL scheme. So basically, they search one level upward, from surface to upward, until the bulk ratius number equals to a critical ratius number. So that's provided by different PBL scheme, like the YSU and GFS. So they use a different value. For the YSU, they're using a critical ratius number equals to 0. That's a purely thermal definition. The shear impact is not included that much. But for the GFS, they're using a large value here. That's a capital within 0.15 to 0.35. That's much greater, larger. The critical ratius number means the diagnosed PBL height is also higher. So that also means the Kn, or the vertical diffusion, is stronger. So that's basically the difference of these two schemes. And so how to verify this like PBL scheme in the hurricane conditions? I will have to give an example about how extreme the hurricane boundary layer is. Yeah, I don't know whether you can hear the sound here. So this is a landfall of the Hurricane Ida. I like this video very much because it's provided a bird view about the turbulent structures. Yeah, from above, you can see like the streaky like structure in the boundary layer. This is typical of the shear-driven boundary layer. It's pretty dangerous for the aircraft to fly that low to sample the data. But we did somehow like 2 decades ago. And an aircraft flying to 450 meters at a constant flight level. So from that flight level data, we established a relationship between the Km and wind. And they use this relationship to cap the maximum Km in the GFS PBL scheme. That was using the hurricane warp model. And they find that like this efforts to reduce the Km substantially improve the forecasted scale, especially the intensity forecast, including the rapid intensification, which is pretty encouraging. But we also mentioned earlier, like the PBL scheme was designed as a single column model. So it's very crucial to derive the profile information in highway conditions. So far, we only have one profile that was located in the large radii from the TC center. That's in the mature hurricane, of course. And that was collected nearly 20 years ago in the Civil-X experiment. And in highway conditions or closer to the TC center, the profile information is entirely missing. So how to fill in this gap here? And we try to use the large-eddy simulation. If one not familiar with what is large-eddy simulation, so simple idea is like it's a numeric simulation with very fine horizontal grid spacings, like on the order of 10 to 100 meters. So with that grid size, most of the turbulent eddies can be directly resolved. And so that's left only of a very tiny portion of turbulence near the surface that need to be addressed by the subgrid scale model. But anyway, so that can just resolve the turbulence pretty well. And so the issue is like hurricane is on the scale of few hundreds kilometers, right? So using the large-eddy simulation for the full TC circulation will be extremely computationally expensive. So we try to using a different large-eddy simulation technique. That's like a small domain. Like typically, like previous studies using that technique to simulate or just develop the PBL scheme. But it's a challenge when we apply this area's technique to hurricane boundary layer. The problem comes from the thermodynamic stations, the conditions. I give an example on the right. That's the potential temperature profile. In this mature hurricanes, the potential temperature profile increases with height. Namely, that's the statically stable. And if we don't do anything to the thermal profiles, we have something like this. It's very deep, well-mixed layer was superimposed by the capped inversion. So that's actually typical about the convective boundary layer. It's not hurricane boundary or something. And that profile also suggests there are excessive vertical mixing here. And anything we derive, like the eddy viscosity or turbulent kinetic energy or some wind profile under this thermodynamic profiles cannot represent the realistic hurricane conditions. So we have to find a way to address that. So we're using a ARS technique. So the ARS was performed under realistic hurricane conditions. And we're using a larger scale nudging technique that can anchor the realistic potential temperature and mixing ratio profiles during the simulation. So that just address this issue. So where these profiles come from? So we got this profile from the dropsum composites of mature hurricanes. And the left panel I just showed in the previous slides. So the upper one is the tangential wind, and the lower one is radial wind. The inflow layer depth typically is around 1 kilometer in mature hurricanes, and it decreases towards the teeth center. And the right panel, the right upper one is the potential temperature structure and the mixing ratio on the bottom. So we extract 3 sets of profiles when the 10-meter tangential wind equals 25, 35, and 45 meters per second. And using these 3 sets of profiles, especially the thermal profiles, to initiate the area simulations. And the model setup is pretty straightforward. Imagine we have virtual teeth circulation, and the shading represents the wind speed of 10 meter at 10 meter height. And so the area's domain was located due east to the teeth center. So the area's domain is very small, about 5 kilometers. So we can use very small horizontal grid spacings. We're using 10 meters, so most of the turbulence can be directly resolved. And this small scale ARS domain was achieved by using a technique developed by Brian et al. 2017. So the main idea is try to find a mesoscale tendency term across this small ARS domain to mimic the real hurricane dynamics. For example, the pressure gradient force, the centrifugal force, and the Coriolis force. And this mesoscale term was shown on the right to 2 equations. Because this is a model domain located due east, so the V, that's the tangential wind, and the U, that will be the radial wind. So the capital V and the capital R, that's something information can be derived from the dropsum composite. The capital V is simply, we can consider this as like a gradient wind. We typically get this information near the top of the boundary because we assume gradient wind balance. And R is the location of ARS domain. And another information is about capital V, partial V over partial R, that's a radial gradient of the gradient wind. And that's also going to be derived from the dropsum composites. So with this, we can specify the vortex structures, and then we do the area simulations. So at the same location, we also run the single column modeling using a different PBL scheme. That's only 1 grid block. So we just integrate the areas and single column modeling forward for 6 hours, and the steady state can be arrived at 2.5 hours. So we average the last 2 hours. The results, we compare the vertical profile of areas and single column modeling. So the black line is areas, so it's in a domain average sense, by the way. And we may be aware that the different PBL scheme work with a different surface layer scheme, right? And we actually made additional efforts to make sure the same GFDL surface layer scheme, which is using the Harkin work model, was used for both areas and single column modeling. And with that, okay, we try to verify the PBL performance. And before that, we actually verify the ARS result first to make sure it's robust and can provide insight into the hurricane boundary. And this plot just shows the momentum stress, the vertical profile of it. The line are from the ARS results, and the dots and squares are coming from the observational data. And it's very encouraging because 3 experiments, the momentum stress was well located within the range of observational data. Of course, there are a few large observational values. Those are collected in the eyewall mission, and they are related to meso vortices. But besides of that, this verification also highlighted another point. That's near the surface layer. We have no data. And in the future, we definitely need to collect more data, probably through the drones in the near surface layer. So that information will be crucial to verify the near surface parameterizations, as well as to verify the ARS results. But anyway, this is just comparison or verification, just show that ARS information can be robust and can provide insight to the boundary of in the hurricane conditions. And we've evaluated the first type of the PBL scheme, as we mentioned earlier, that's the KPP PBL scheme, the K profile. And the 3 panels show 3 experiments, V25, V35, and V45. The diagnosed PBL height from the ARS was provided top of each panel. So basically, the PBL height in the ARS can be seen as the minimum value of the KM. So that's where we get this value. And we verify the analytical KPP profile because we provide feeding the KPP scheme with the accurate U star and PBL height from the areas. So the logic here is like, if we provided these two information to the KPP scheme as shown by this equation here, if the KPP scheme is robust, they can reproduce areas profile, right? So that's the reasoning here. And so we just look at this, the long dashed line here. That's a typical because shear parameter equals to 2. So remember, so the PBL height is 1 kilometer, so the basically position, the maximum came at near 300 meters. So that's what we saw here. It's much higher compared to the areas. And meanwhile, the magnitude of the maximum KN is also larger compared to the areas result. And so we try to increase the shear parameters. So like to the 4. So that would position the maximum KN at 200 meters because of 1/5 of the diagnostic PBL height. And but anyway, we find in high wind conditions above that level, the KN value was substantially underestimated. So this result basically demonstrates that the KPP scheme is inherently flawed in hurricane conditions. And we actually verify and evaluate the PBL scheme, the YSU and the GFS, these two PBL scheme and KPP scheme. So we mentioned earlier, there are many differences in their diagnostic PBL height. So GFS have a higher PBL height, so the vertical diffusion is larger. So that's why we see 3 experiments. The red line is the GFS. So the inflow layer depth is typically the highest compared to the other schemes, and is even higher compared to the areas. So it's robust in the 3 experiments. But YSU just did the opposite because the PBL height is very shallow, and the inflow layer depth is the shallowest in all the 3 schemes shown here, and the inflow strength is also much stronger near the surface. And another issue we find from the YSU is the near surface. And the 10-meter wind in the high wind conditions is showing a high bias. Yeah, we have communication with EMC colleagues, and this is potentially the reason why when they're using the YSU, sometimes they find a high bias of the wind near the surface. But anyway, there's an encouraging result in this plot is the orange line, that's M1N scheme. And we find that the inflow layer depth in different experiments is comparable to the areas, right? And the tangential wind profile is also reasonable. And I'm just curious what's going on, why this scheme can perform better compared to the others. And so M1N is a high order scheme or 1.5 order. It's different to the KPP because it have a prognostic equation for the turbulence kinetic energy and some other high moment turbulence variables. And the KN we still parameterize for the basic idea is proportional to the mixed length L. That's the characteristic length scale or the most energy containing eddy size. And also proportional to the TKE, that's a measure of turbulent intensity, right? And the additional term on the right, that'll be the stability function, like the thermodynamic conditions can further modify the KN profile. So but anyway, like the key part of the high order PBL scheme, of course, the TKE is flow dependent. It have prognostic equations, right? That seems like more physically reasonable. And another advantage is about mixed length parameterization here, the L. The L is a blending of 3 length scale in the boundary layer of the M1 scheme. So the first one is the LS, that's a surface level length scale. Yeah, so from the math, by the way. So the L was determined by the minimum value of the 3 of these length scales. So that's from the math. So whichever is the smallest, it will dominant value, and it will be pass this value to the mixed length. So the LS is surface length scale, and we saw this earlier. It's a comma constant times Z. That's the neutral conditions mixed length, right? And we'll have additional polynomial term on the right. That's actually the stability function. So with this additional term, that can be like extend the mixed length to the broader scale, to the stable or unstable conditions. So make it applicable in all the different conditions beyond the neutral. And the important variable here will be the LT. So LT, that's the definition is like the vertical integral of TKE times Z divided by the vertical integral of the TKE. So we can understand this as approximation of the mean size of turbulent eddies in the PBL. This is a very important eddy scale, like in the hurricane boundary. And ALB, that's the buoyancy length scale. Typically, this is not that important in the hurricane conditions. I will give an example about the M1 scheme in the V25. V25. Oh yeah. So what is L4? That's the coefficient. So that's the coefficient to before the stability function. That's based on the tuning, which fits the better. And the V25 experiment, the mixed lens performance, I show the results here. The orange line, that's the mixed lens on the left. And LS, that's the surface length scale, the gray line. And ALT is a vertical integral, basically it's a constant value. And it's nearly 40 meters, but anyway, this value or the mixed length is within the range of observational data from John and Drainer, so it's pretty encouraging. And we find there are two different turbulence regimes, one in the near surface layer. The mixed length of the MOI was determined or dominated by the LS, that's a surface length scale. Above that, that's the LT, turbulent length scale. And the interesting phenomenon here is like both the MOI and the observation show that above like 150 meters, the mixed length does not vary that much with height, right? And so what causing that? So we dig into the previous literature, try to find some evidence. And there's some additional variable, turbulence variable here. So that's the sigma VU and cubic. This is actually the velocity difference across the distance r. And so we have to pay more attention about the sign of this variable. If the sign is negative, so that basically means this is a forward scattering, means the energy was transferred from the larger scale to the smaller scale. So that's the 3D turbulence characteristics, as we mentioned earlier. But an inverse process was shown by the positive value here. So energy was converted back from smaller scale to a relatively larger scale. And that's the 2D turbulence characteristics. And this data was collected at different flight levels of the P3 aircraft. And we find a separation level near the 150 meters. So below that, that's a 3D turbulence, and above that, that's 2D turbulence, right? And we hypothesize that the nearly constant mixed length above the surface layer is probably the characteristics of the 2D turbulence. And of course, in the future, we need to collect more data to verify these assumptions. And we also pay attention to another high-order PBL scheme. We call it the EDMF-TKE scheme. So we study that because it's used in the next generation hurricane forecasting model from NOAA. We call it HAFS, Hurricane Analysis and Forecast System. And so this is also a high order PBL scheme. But the mixing length, especially the mixing length, is different. The parameterization is different. It's a two-length scale of lengthening on the right. The surface layer length scale is very similar, but LBL, that's a Bolak length scale. That's basically prescribed the mixed length above the surface layer. And its definition is further determined by the minimum value of the error up and error down. So you may wonder, what's this? Like, yeah, this is basically like we're given a parcel at a specific height have the TKE turbulent kinetic energy, right? It can move up and down. So how the motion can be stopped? That's basically what this length scale means. So the vertical motion can be stopped by two effects. One is stratification effect. Like the stable conditions, stable thermodynamic profiles can stop because they have negative buoyancy. And also we have the shear impact. So the shear impact, like the shear can distort the rising plume in the boundary layer. So that can also weaken the turbulent kinetic energy. So that's how the physics works here. And this physically looks very promising that the issue here is that the Bolak mixed length was capped at 300 meters. So that's typical for the convective boundary layer, but it's a little too much for the hurricane boundary layers. I will give you an example here. And then we compare the EDMF-TKE scheme with the MOIN in the V45 experiments. And the black line is still the areas, the orange line is MOIN, and the green line is EDMF-TKE. And the left panel shows the eddy viscosity, the KM profile. The right one is the turbulence kinetic energy. And we find the MOIN did pretty good job, especially in the lower to middle boundary layers. But in contrast, the EDMF-TKE show a factor of 2 greater in terms of the maximum KM in the hurricane conditions. And that's come from the reason I mentioned earlier. The maximum the Bolak mixed length was capped at 300 meters. That's way too much. Remember, in MOIN, we show something near the 40 to 50 meters. And for the V45, the TKE profile, the MOIN still did a pretty good job. It's very similar to the ARIS results. But EDMF-TKE like have a high bias below the 600 meters, and is at near the surface is actually a factor of 2 greater compared to the ARIS. That's a very notable high bias because TKE was determined by the TKE shear generation in the surface and also plus the minus the TKE dissipation by the friction, right? So that basically means the TKE generation and dissipation is not balanced in this scheme, and we need to pay attention to that. So we try to do something here, and we find out like the PBL and surface parameterization is not matched. So that's the main issue about this scheme. And we demonstrate that, like, so for the PBL scheme, if we assume neutral conditions, that's generally applicable to the hurricane boundary, especially in lower middle boundaries. And we assume like the length scale using the KM and this TK dispersion is the same, right? So the CM is actually, we showed earlier, that's using the KM formulation of the EDMF-TKE scheme. CD, that's not the CD in the surface layer, just be clarified. This is a CD was using the TK dispersion term in the PBL scheme. And S, that's the shear, LK will be the mixed length, basically. We assume they are equal. And so PBL, we assume the TK generation by shear was balanced by the TK dispersion. So that's how we derive this formulation here. But for the surface layer, actually we can do something similar. So we assume the TK generation balanced by the dispersion, the KM will be equal to LK squared times shear. So to match the PBL and surface layer parameterization, this full formulation need to be equal or just same, right? So that basically determines that the CM cubic will be equal to CD. So the job next is try to determine the value of the CD, so we can just determine another CM value. But in the original EDMF-TKE, the CM and CD was 0.4. Obviously, this value is not satisfied. And also a caveat here is that they're using a different length scale for dispersion and KM. But in that situation, we cannot or have no idea like how to derive this relationship to make sure the PBL is in balance with the surface layer. And so we derive the CD formation from the areas, and the value will be the 0.12. And that also can get us to get information of the CM. So this mismatch issue was solved by this change. And we have additional modification. And oh, by the way, so when this is basically a neutral condition, people maybe wonder why, how can it be applied to the unstable and stable boundary conditions, right? So actually in the surface layer, they have the Morning optical similarity theory that can extend the neutral conditions to the unstable or stable boundary conditions. And the additional change, the second change we made is about mixed length. So the areas, the mixed length was defined as KM divided by shear and root mean square. That's actually also the same formulation for the observational data from Chen in 2012. And the 3 experiments show some of the maximum of the mixed length will be near 40 to 50 meters. And that's much smaller than the 300 meters we mentioned earlier. So that's an important change here. So we next change, we're using the symptotic length scale based on areas and observations. So the scale is less than 100 meters. But we have to remind them, like, we only use this change for the movingness in the HAFS model. That basically means we only use this capped less than 100 meters symptotic length scale in the hurricane conditions. So that won't affect the global scale. And the additional change will be for the high wind conditions. So we adopt a new PBL high definition that works better in the high wind conditions. Yeah, so the original one, we remember earlier we mentioned about the bulk ratios number calculated from the surface to a specific model level, right? With that, PBL high definition is not work very well in high wind conditions because of the dominant shear impact below the first model level. So that shear effect is so dominant to make the bulk ratio number extremely small. And then we adopt the new PBL high definition, follow the previous literature. So that idea was to calculate the bulk ratios number from the first model level rather than from the surface, all the way upward until the critical ratios number was satisfied. So that makes the diagnosed PBL high much lower and more comparable to the observations. An additional change here will be tapering the mass fluxes because this is EDMF. ED is eddy diffusivity. It's related to the KM. And there's MF, that's actually the mass flux. So there's an additional component there. So we taper that in high wind conditions below 20 meters. Basically to represent like the shear impact can distort the rising plumes, as we mentioned earlier. And with this change 1 to 4, so the TKE profile was the modified EDMF-TKE was shown by the red line in these plots, and our TKE values on the top panels and KM in lower panels. So the TK profile and KM values become much better compared to the areas. And not surprisingly, the inflow layer structures, the red line show the upper panels and also the tangential wind profiles agrees much better compared to the original one. This is our very encouraging results, but these are limited by its single column model. People will wonder how the realistic 3D simulations looks like. So we did that. And we incorporate this modified EDMF-TKE scheme into the HAFS. Now it can be a nameless switch of TC PBL can easily turn on and turn off these applications. So we appreciate Bing Liu and the Chen from EMC for the related help. And so here's a simulation of the Hurricane Michael. And this is Ensemble, basically the Ensemble based on different initialization time. So each experiment, the blue one will be using the blue colors using the original EDMF-TKE. The red color is still the modified EDMF-TKE. So each one have like 5 members. And clearly the red line have a, so tracking performance is similar, but for the intensity plot on the upper right here, it's in RI occurs much earlier. So that's more consistent with the best track, the dashed gray line here. But for the blue line, the RM step is much delayed, and the maximum intensity is much weaker compared to the best track. So that's the RA performance. So with the modified PBL scheme, it's much better. And before the landfall, near the 36 hours, and the smaller radius mass wind was actually captured better by the modified PBL scheme as well. So this is very encouraging. So we may wonder what causes that. So we examine the boundary structure near the bifurcation point near the 18 hours here, or 21 hours. So we have a 6-hour average to compare the boundary structure to explain what's going on here. And we show the PBL structure here. Left panel was original PBL scheme, and middle will be the modified. And the panel C will be the difference, the control minus the REV, and the revised experiments. And the shading here means the boundary inflow. So clearly the revised or modified TKE induced stronger boundary inflow just outside the radius mass wind, as shown by the black line in these panels here. And so within the 1 time to 3 times the maximum radius mass wind, so the radial inflow is all enhanced. So the stronger boundary inflow will affect the absolute angular momentum into the smaller radii, which can spin up the TC circulation more effectively. And that's explain why the RF forecast is getting better. And another change, you remember, like we changed the PBL high definition, right? So that's the gray line shown in each panel. So by using the new PBL definition, the PBL high was lower substantially. At this stage, the vortex is still weak. So that difference can be even more notable when in a stronger intensity. But anyway, with this change, we find the inflow layer depth was marked by the -1 meter per second, the blue dashed line in the 2 experiments, right? And become more comparable with the modified PBL height. That's another aspect to demonstrate the PBL height definition works better in a high wind condition. And that's something encouragement here. And I want to remind that, so this RA performance is not standalone. So we actually examine all the cases during the 2021 North Atlantic hurricane season. So we verify the RF forecasted still. And here the HAFS A, that's blue. The blue star here is the HAFS using the original PBL scheme. HAFS Y is using the modified PBL scheme. And clearly the red star have a higher probability of detection. And meanwhile, the force alarm rate was slightly reduced. So that's based on a much larger sample compared to the single case before. So that's robust. Like the RF forecast skill was improved using the the modified PBL scheme. And we also remind that we're using a different RF definition, slightly different, but it's still one RF criteria in the ship's model. So in the ship's model, so we're using 25 knots over 24 hours because we consider about the intrinsic error in the best track. So there's some uncertainty inside. So we consider that part in this verification plot. Anyway, the results is very encouraging. And this improved RF forecast was contributed by the better structure representation in the forecast. So we show the sample size at each top of the panel. And the red line here is still the modified EDMF-TKE scheme. And we find that either for the radius mass wind, the hurricane force radii, and the gale force wind radii, so the bias was all reduced, right? So it's have a smaller bias. So the structure generally was better represented in this HAFS Y experiments. And meanwhile, the intensity, the weak bias here, the weak bias was reduced by using the modified PBL scheme. And either the Vmax or the minimum pressure shown in the panel E here. So the only compromise here is about the cross-track bias. So it's at longer release time, it started getting larger. And so we noted that this actually was contributed by a few, anomalous cases. I will introduce this later. But in general, and compared to the original PBL, the revised PBL scheme showed advantage in both intensity and structure forecast, which is slightly, but meanwhile show a slightly higher bias, right of track bias at longer lead time. And the discussion about the why the degradation of the track scale is how that happened. Like. And we just verify the track scale of the mean absolute error of the both the HAFS A was shown by the blue line. That's the benchmark. So that's the relative difference compared to HAFS A. So the red line shows the HAFS Y experiment using the modified PBL scheme. And we find the degradation of the track scale increases with forecast hours, right? So there's a tendency to increase with time. So, and that's interesting because we find this tendency was actually contributed by only a few anomalous cases of Hurricane Henry. And I just show you an example about the HAFS A on the left, HAFS Y in the middle. And you can see the early 4 cycles. The right of track bias is substantial. Actually, at the 4-day, 96 hour, the track error of HAFS Y of this field's cases can be over 400 nautical miles. So that's very large bias and can contribute to this tendency. By just removing these 4 cycles, we can see the tendency was removed. And the track scale degradation is just on average about 5%. But meanwhile, without these 4 early cycles, the intensity scale was improved and extends to a longer time, about 4.5 days. So this is very encouraging. But why the results can be so sensitive to so why they can be 2 to 4 early cycles? So what caused this large right of track bias of Henry? And we actually just did another sensitivity test by turning off the cumulative scheme. Just remember, HAFS also using the scale-aware cumulative scheme, even it's about 2 and 3 kilometers resolution. This is on top of the HAFS Y. So we can find the right of track bias was substantially reduced with this change. And actually, even the intensity forecast gets better. We didn't show that here, but that's the results. So why the right of track bias is very sensitive to cumulative schemes? Yeah, that's something we need to figure out. Definitely the scale-aware parameterization need to be examined, right? And also like how that physical processes was represented in the cumulative scheme. So to me, another issue just pops out after digging deeper about this issue. As I mentioned earlier, the PBL scheme, EDMF, was composed by the eddy diffusivity part, which will have been addressed well in the area's changes. And the addition of its mass flux component on the right. So the middle one will be the surface-driven mass fluxes, and the rightmost is the stratocumulus top-driven. That's the radiative coating-induced mass fluxes, typically near the top of the boundary layer, and that is relatively small compared to the surface layer mass fluxes. So we neglect that in this discussion. And we just show the surface-driven mass fluxes, and this panel just showed axisymmetric structure of the 3D simulations, like so the shading represents the surface-driven mass flux. And the black contour, that's the axisymmetric tangential wind. And we have found that when the surface axisymmetric tangential wind is like 30 meters per second, or in the hurricane force wind, the mass flux is still substantial, and it can extend all the way to the 2 kilometers. But meanwhile, I also show the cloud vapor mixing ratio. So this is a 0.01 gram per kilogram, typically denotes the bottom cloud base. So this mass flux extends very well into the shallow cumulus, right? So remember, in the shallow cumulus scheme, the cloud depth is only about 450 to 200 meter bar. So there's an existing like double counting in the cloudy boundary layers. This is something need to be unified and addressed in the future. Because typically as a EDMF-TKE, the mass flux idea is coming from the cumulative scheme. So it should be able to handle the rising convective plume below the subcloud layers. And then this part of these plumes will be converted to the core of the convective outdrops. That's a smaller fraction. But this is continuous processes. And we need to do that. And we need to do that like can be handled by the PBL scheme itself. So there's no need to call a shallow cumulative scheme afterwards. So that's some kind of like a task for the future, the UFS plus one, the physics development. And another issue we want to mention is the representation of the eyewall turbulence. And MIN is, I mentioned that it's a TKE based high order PBL scheme. So the TKE actually is treated as a tracer in the model. So it can be affected by the eyewall updraft, as shown by this red contour here. And the control simulation on the left will be with the TKE deflection. So the right panel B will be without TKE deflection. So with TKE deflection, the TKE, the large value in the eyewall, can extend to a higher value. And actually, this is better with the P3 airborne Doppler radar, the observations. So there's large TKE values in the eyewall. And we don't show the results here, but the TKE direction also contributes to the formation of stronger and also smaller inner core. So for the TC modeling, this term cannot be like neglected. So typically, we should encourage people to include this term in the hurricane simulations. And but it's another story for the EDMF-TKE. So in HAFS, the TKE direction is turned on by default. That we just output the 3D simulation axisymmetric structure similar to the previous slide. And without TKE direction, the TKE column in the eyewall is only extensive of 2 kilometers. And even with TKE direction, it's still less than 4 kilometers. It's much shallower compared to the MYN. And we did try to find out what's going on here. And we focus on the red line here because this is modified EDMF-TKE we did. And black line is MYN. So below the 700 or 700 meters, the mixed lengths between the two schemes is very similar, but what differs is about. The MYN have a much greater mixed lengths above that. Now remember, the Km is proportional to mixed lengths, right? So that's also the shear production. The large mixed lengths mean the shear production is stronger in the MYN. Also, the dissipation is weaker. So that's explaining they have large TKE values even above the inflow layer in the eyewall region. But for the modified TKE, the TKE's value is smaller because the mixed length is small, so the dissipation is very small. But meanwhile, the generation dissipation is very large. But meanwhile, the generation term is also very small. So that explains the difference here. So another effort for the future PBL development will address the PBL vertical diffusion above the diagnosed PBL height in the eyewall region, especially in the cloudy layers. Yeah, that's some of the future work here. Okay, so I don't have too much time, but I just want to summarize here. So we propose a modeling framework, including a simple nudging term to anchor the thermal profiles. So that just allows a fair apple-to-apple comparison and can show some insight on how the PBL scheme perform in hurricane conditions. And generally, areas produce very robust information, so we use that to evaluate like 2 types of PBL scheme. The first order PBL scheme, the K-profile parameterization scheme, we find is inherently flowing and simulating TC boundary layer. MON is recommended based on the results because it's high order closure, so the TKE is flow dependent variable. So the mixed length parameterization is very sophisticated. And most importantly, it also include the option to include the TK direction that address the large TKH value in the eyewall pretty well. And the original EDMF-TKE scheme, it's like does not perform pretty well because of the high values of TK in the lower boundary layer. And we find it's mainly because of the mismatched surface layer and PBL parameterizations. And also the mixed length above the surface layer is overestimated. The 300 meters is way too large. And we improved that. And now this improved PBL scheme was incorporated into the HAFS. And so the modified PBL scheme can accelerate the boundary inflow within the 3 times of radius mass moving or the inner core region. So that can contribute to the stronger TC intensity and a smaller radius mass moving. And we examined the HAFS forecast over 2021 hurricane season. The forecast scale of intensity and structure is improved. Yeah, so the track scale is slightly degraded, but it's mostly contributed by field early cycles in Henry. And that motivates us to further pursue the unification of mass fluxes in the EDMF PBL scheme and the shallow cumulus scheme. And the last part will be like for the EDMF-TKE, the eyewall TKE column remains shallow. So we have to address the mixed length parameterizations above the diagnosed PBL height, especially in the cloudy layer. And that's all I have today. Thanks for attention.
Thank you, Xiaomin. Thank you, Dr. Chen. With the sake of time, we will just take 1 or 2 questions, and I will open up the chat in case there are any there. There's a question by Young Suk. What is A4 in LS?
Yeah, I expect
he answered it.
That's a coefficient between the stability factor. So it's just using different value for the unstable and stable conditions.
But is it empirically driven values exist?
I think that's tuned based on the areas, like previous areas results. So that's what they use in the surface layer length scale.
Mm-hmm.
And there's another question here for you, Dr. Chen.
Yeah, I don't know what that means. Like you simulate the profile, you mean the Oh, you mean the areas profile, right? Or the PBL profiles? So
Hey, Xiaomin,
yeah, go ahead.
Xiaomin, can you hear me? Yeah, I find your observation have a large uncertainty in horizontal, and so I wonder how large uncertainty of your simulated profile. I see only show the one profile for one scheme. So I don't wonder what the uncertainty of the simulated profile can represent the observed uncertainty. Yes.
You mean the area simulated, right?
Yeah, areas and also other PBL scheme.
Yeah, PBL scheme.
Only so,
PBL scheme.
so you only saw the mean profile or the 50% tie profile, right?
Okay, I got you. Yeah, so the we didn't show the standard deviation, especially like along the mean values. So actually, that especially for the areas is temporal average. So we have the standard deviation. That's value typically is very small. Like it's just along the each side about like 10 to 15% about the mean value. So that's the within the range. Like is it comparable to the observations? Yeah, we just didn't show that. Yeah, thanks for asking about that.
Thank you.
Yeah. Okay, Rob.
So I'll just read the question. It says, could you remotely sense fields from model PBL scheme evaluations in addition to drone data, thinking maybe TDR profiles or IRAP?
Yeah, Rob, that's an excellent question. Like, yeah, so we just showed the Lorsolo's paper. That's the TDR retrieval of TKE. So that was done like a decade ago. And right now we have final resolution like the IRAP. Yeah, definitely provide like a lot more detail about TKE structure in the boundary layer. Yeah, so we were trying to figure out a way to verify that. But that data is very useful, I believe.
Yeah, that's good. Thanks, Xiaomin. I mean, obviously the drone data is great too, especially for thermo, which you can't get.
Yes.
But yeah, okay, thanks.
All right, thank you, everyone. We're very close to time, so we'll go ahead and close. In case you missed any of this presentation, it'll be recorded and it'll be available on our website in a couple of days in our YouTube channel. So thank you, everyone. Good luck to you, Xiaomin. Everyone, have a good day. Thank you.
Thank you, everyone.